Hi, welcome back to chapters 13 and 14. Mr. Dalton and his atoms. Perhaps you feel that you will never get anywhere in life because you are not rich, or you are tall and lanky like a walking vine, or you have a very gruff voice, and even worse, people start yawning and leaving the room when you speak. Or maybe your chin and your nose are both so long and pointed that they almost touch each other. Perhaps you are colorblind, and maybe you are so busy that you cannot get your work done properly. If you had one or two of these problems, you might consider yourself quite unfortunate. But if you had all of these problems, you would be John Dalton, one of the most famous chemists of all time, and the founder of the modern atomic theory in chemistry. So keep that in mind. John Dalton was born in Eaglesfield, England, the son of a poor weaver. He, like his father, was a Quaker. From the time he was very young, John Dalton had to make his way in the world. He was largely self-educated and earned his living for much of his life by teaching. In fact, he began to teach school when he was just 12. Perhaps Dalton's most helpful trait was his perseverance. In the race to make chemical discoveries, there are tortoises and there are hares. And Mr. Dalton, by his own admission, was a tortoise, a very diligent one, too. For example, he began to keep a daily journal called Observations on the Weather in 1787, where he wrote down everything and anything he could about the rain, the snow, and for the atmospheric pressure, the levels of water vapor in the air, and so on. He plodded all over England with his thermometer and barometer, up hills and down into valleys, through the bogs and into the forest, and he did it for 57 more years. The last journal entry was the night before he died. That is perseverance, and such perseverance paid off, because his observations on the action of gases in the atmosphere led him to formulate his atomic theory. Dalton learned about atoms when he studied Sir Isaac Newton's works. A little over a century before Dalton, Newton had used the corpuscle philosophy, and atomism was called, to explain and predict the way the planets and stars moved, as well as how the tides here on Earth worked. Dalton also read Boyle, and so had heard about atoms from him. He was even more familiar with those ancient atomists, Democritus, Epicurus, and Lucretius. But none of these men had ever seen an atom, for if atoms existed, they were much, much too small to see, nor had any of these men proven that atoms existed. Therefore, none of these men could satisfy so practical a person as Mr. John Dalton. So while Dalton did believe that atoms existed, he wanted this belief to rest on a much more solid foundation. If we look at what is old and new in Dalton's theory, we will see how he tried to build those foundations. He supposed that all matter, all physical stuff, however big or small, was made of solid, indestructible, indivisible atoms. He used little wood spears to represent them when he taught. But this was not new. All the Thomasists, ancient and modern, thought that. He assumed that they were as many different kinds of atoms as there were elements, for him about 50 at the time. That was new from the previous atomists. Both ancient and modern thought that all atoms were made of the same universal stuff, and differed only in the size and shape. But Dalton thought that there were hydrogen atoms and oxygen atoms and sulfur atoms and so on down the line. Okay, this is how he invented the symbols for each one. He also thought that the reason chemical combinations occurred in ratios of whole numbers by weight, the law of definite proportions given to us by Proust, was that the whole numbers ultimately stood for individual atoms. Of course, that was very new and very important. So if you said to Mr. Dunn, "Good sir, why is there exactly twice as many oxygen by weight in carbonic acid as there is in carbonic oxide?" he would reply, "Very simple. But there is twice as many oxygen atoms in carbonic acid." This was called the law of multiple proportions, which states in Dalton's words, in the formation of two or more compounds from the same element, the weights of one element that combine with the fixed weight of a second element are in a ratio of small whole numbers or integers, such as 2 to 1, 3 to 1, 3 to 2, or 4 to 3, and even thought from this that he could weigh the atoms. That was very, very new and seemingly impossible dream. Let's look more closely at the last 2 points. Recall that Proust found that chemical compounds made of the same elements were ruled by very exact formula, but he also found that they always occurred in whole number multiples. Dalton set out to explain why the formulas were so exact. Here we must remember that Dalton was not looking at the chemical formula we have today, such as CH4 or C2H2. With these, you can tell very quickly that the first has 1 atom of carbon and 4 atoms of hydrogen, and the second has 2 carbon atoms and 4 hydrogen atoms. These symbols were invented because of Dalton's theory. All Dalton himself had were the chemical names used at the time, such as carburetted hydrogen and Ophiolite gas. Dalton, like Proust, noticed that the 2 elements could combine to form 2 distinct chemical compounds. For instance, Dalton noticed that carbon and hydrogen could form Oliphant gas, but the hydrogen was doubled. He got something else, carburetted hydrogen. Thought Dalton, what does that mean? And he wrote down this in his notebook. Oliphant gas, and then this, carbonated hydrogen. The black dot was Dalton's symbol for carbon atom. The white circle with a dot was Dalton's symbol for hydrogen atom. When he put them next to each other, it meant that the atoms were linked as elements in a compound. So a big jar full of compound carburetted hydrogen was, so Dalton said, made up of thousands or maybe millions, and there were twice as many of the hydrogens in the glass jar as there would be in the same jar filled with an equal amount of the hydrogen and the carbons. If you don't believe him, well, just count for yourself. So you can look in these 2. This was an enormous leap for chemistry, even if it was a leap of faith, for he still had not seen an atom, but the leap explained why chemical combinations were so very regular. Different compounds made of the same elements differed by the number of atoms. Each atom, we might say, stands for a whole number. This is why today, for example, we write CH4 for methane and C2H4 for ethane. But forgive us for pointing this out, Mr. Dalton. In getting things right in one way, Dalton managed to get them wrong in another. Ophiolite gas is today called ethane, and carburetted hydrogen is now called methane. What's wrong? Dalton thought that the carburetted hydrogen, methane, had twice as many hydrogens as Oliphant gas, ethane. But if you look at our modern formula, you can see that they both have the exact same amount of hydrogen atoms. For the truth of the matter was that Oliphant gas had twice the carbon, not half the hydrogen. Even more important, he had the total number of atoms in each compound wrong. Oliphant gas actually had 2 carbon atoms and 4 hydrogen atoms, not as Dalton thought, 1 carbon and 1 hydrogen atom. And carburetted hydrogen, methane, had 1 carbon and 4 hydrogens, not as Dalton thought, 1 carbon and 2 hydrogens. So we might say that Dalton got it right, but in the wrong way, or he got it right, but he got it wrong, but in the right way. In either case, however, even if he did not get the compounds exactly right all the time, Dalton's general idea of atomism led chemistry toward thinking of the elements in terms of distinct atoms, which is how they appear in the periodic table and in our chemical formulae. Even so, we should ask what caused Dalton to get the wrong number of atoms in each case. As we shall see in the next chapter, the error lay in trying to determine the number of atoms by the weight of each of the separate elements in the compound. Having said this, however, we must not leap to the conclusion that using weight was a bad idea, an idea which could only lead to error. In fact, it was a very good idea, and ironically led to the correction of the problem of using weight. Sometimes the only way out of the forest is a winding path. Let's follow that important path right now. Atoms, Dalton thought, must have weight. But how could he possibly weigh them? He knew he could not put these tiniest of things on a scale, but he thought he could figure out the relative weight. And even if the relative weights of the atoms were not turned out exactly as Dalton had calculated, still, if we look at the periodic table, we see atomic weight. So if Dalton had not tried to weigh the atoms, at least indirectly, we would have never gotten to the periodic table. So how did he do it? And what is relative weight? Well, pretend that you have a big box of the smallest possible black and white marbles, too small and too many to either weigh or to count one by one. All that you know is that for every white marble, there was one black marble, and also had a magic marble sorter which could put all the white marbles in one bucket and all the black marbles in another. If the marbles are, as we said, too many and too small to weigh and count directly, you could do it indirectly. Yes, you could. Suppose the bucket of white marbles weighed 10 pounds and the bucket of black marbles weighed 20 pounds. Since you know that they are exactly the same number of white marbles as black marbles, you know that each of the black marbles must weigh twice as much as the white marbles. You do not know how much the white marble itself weighs, but you know the weight of the black marbles relative to the white marbles. This is an example of relative weight. Dalton reasoned that the very same way with atoms. Well, using its symbols, if we know the atomic formula for water is hydrogen and oxygen, and we have a certain amount in the jar, we can separate it by all the O's with circles in the center and all the dark O's, and weigh each other. Now, as we have seen above, Dalton used the circle with the dot inside to symbolize hydrogen, and hydrogen was the lightest element. So Dalton weighed everything relative to hydrogen. He used hydrogen the same way or the same weight as he used the white marbles above. The other symbol with the dark zero was a symbol for oxygen. So we calculated the relative weights of oxygen and hydrogen are fairly simple. Dalton used the best measurement for the amount of hydrogen and oxygen and water available at the time. According to Lavoisier, water was 15% hydrogen and 85% oxygen by weight. That is, hydrogen and oxygen, the hydrogen atom made up 15% in the entire weight, and the oxygen atom made up 85%. And so Dalton simply divided 85 by 15 and declared that an oxygen atom weighed 5.5 times as much as a hydrogen atom. Later, Dalton used the more accurate figures of another chemist, Joseph Gay-Lussac, who determined that water was 12.6 parts hydrogen and 87.4 parts oxygen by weight, and so Dalton got the relative weight at 6.94, which he rounded up to 7. Then he proceeded to weigh other compounds and determine the weight of other elements in relation to hydrogen, and he kept figuring and refiguring these atomic weights the rest of his life. Brilliant! But forgive us again, Mr. Dalton, even though it was the right idea, it was not very accurate. Chemists soon found out that water was made up of 2 hydrogen atoms and not 1, and found ways to measure far more accurately. The calculations of Mr. Dalton then are not used any longer, but again, his ideas about the way to measure led ultimately to the atomic weights you see on the periodic table. Finally, we note that Mr. Dalton's symbols are no longer with us either. Not many chemists use his dot symbols, but the idea of using symbols to represent the atoms of an element, rather than just using a general name for the element, stayed with us. Such symbols allowed chemists to represent all kinds of complex chemical reactions and formulae in a very compact, short-handed way. It was a man named Jöns Jaques Berzelius who got the idea of representing atoms by letters. It was he who gave us O for oxygen, C for carbon, CO for cobalt, S for sulfur, and so on. But even though Berzelius and told chemists in 1813 that this was the best way to symbolize the chemicals, it took about 50 years for chemists to accept his letter symbols and use them regularly. But they are, with a few exceptions, the symbols we use today. Dalton did not like Berzelius' letter symbols, however, not in the least. In fact, he hated them. Berzelius' symbols are horrifying, he steamed. The same year he became so angry while discussing Berzelius' symbols with a visitor that he had a stroke. Berzelius' symbols won out anyway, and despite the disagreement, if we take the accomplishments of Dalton and Berzelius together, we are much, much closer to having our modern-day periodic table. But being closer is different from having arrived. So on we go to the next step. 14. The shocking Mr. Davy. We said in the last chapter that in the race to make chemicals discovery, there are tortoises and hares. Mr. Dalton was a tortoise. Now we shall meet a hare, the dashing and rather shocking Sir Humphrey Davy, a native of Cornwall, England. Like Dalton, Davy was poor, the son of a poor farmer, who could have been rich if only a wealthy uncle had not left his will unsigned. So Davy's father stayed poor, and so did young Humphrey. But young Humphrey would not be satisfied with the life of a near penniless farmer. He became an apprentice to Mr. John Borlase, a surgeon apothecary. But Davy would not become a doctor, for a copy of Lavoisier's Elements of Chemist fell into his hands. Soon enough, Davy was discharged from Mr. Borlase's services because of his habit of performing explosive experiments. After his dismissal, Davy met Mr. Thomas Beddoes, who was convinced that the various kinds of gases that had recently been discovered or created might be of some medical benefit. Beddoes founded the Pneumatic Institute and convinced Davy to be his assistant. Davy's daring, even foolhardy disregard for his own safety in his quest for chemical knowledge nearly ended in his early demise. He performed all kinds of quite dangerous experiments for the Institute, inhaling a quite variety of gases, some of which almost caused his suffocation. His most famous discovery, or at least the discovery that first brought him fame, was that inhalation of nitrous oxide had rather strange effects. A thrilling, extended from the chest to the extremities, was almost immediately produced, reported Davy. The more popular name of nitrous oxide is laughing gas. Unlike Mr. Presley, who thought inhaling pure oxygen might tempt people to live out their lives too fast, Mr. Davy was all too happy to promote the use of nitrous oxide merely for its strange physical effects. Soon he was quite famous. But more serious things than laughing gas lay ahead for Davy. The very same year, 1800, that he published his research on nitrous oxide, an Italian physicist, Alessandro Volta, published a paper describing the production of a continuously electrical current from a pile of alternating silver and zinc discs separated by blotting paper soaked in salt water. The larger the pile, the stronger the current. Now, this great voltaic piles of alternating metals, or batteries as they came to be called, were found to have very curious effects on chemical compounds, an effect which would not only lead to the discovery of more elements, but to the very inner secrets governing the entire order of the periodic table of elements. The electric current decomposed chemical compounds. It was soon found that the electrical current running from the pile through wires was applied to water. The water was decomposed into oxygen and hydrogen, and the hydrogen went to the negative pole, and the oxygen went to the positive pole. Davy applied the voltaic pile to various minerals and found that the current decomposed these minerals into alkalis or bases and acids. The alkalis cling to the negative pole and the acids to the positive poles. Perhaps, thought Davy, we can shock apart the alkalis themselves, especially the ones that had resisted any attempts by chemicals to break them down further. He seized the voltaic piles and used them like battery rams to break down these stubborn alkalis. First, potash, which many thought was itself an element. David hooked the voltaic pile to moistened caustic potash. Very soon, Davy tells us, small globulars have high metallic luster, similar to mercury, appeared at the negative pole. He could not contain his joy. As his cousin and assistant later reported, he actually danced about the room in ecstatic delight. Some little time was required for him to compose himself to continue the experiment, and he called this new metallic element potassium. 2 days later, he was about to decompose caustic soda, another alkali, and discovered another metallic element, which he named sodium. Then next he charged at magnesium, lime, or calx, strontium, borates, and discovered further metallic elements such as he named magnesium, calcium, strontium, and barium. Davy also used the voltaic pile to prove that muriatic acid, which Lavoisier thought to be some kind of acid formed with oxygen, was actually an element. He did it by showing that no matter how hard he tried, he could not break down muriatic acid with an electric current. He declared it to be an element and named it selene. Certainly discovering all these elements was a grand thing, but even grander discovery was in store. The effects of electricity on compounds made Davy suspect that since an electric current broke down chemical bonds, the chemical bonds themselves must somehow be electrical in nature. If electrolysis, that is, The use of electric current to decompose a compound caused elements and compounds to be attracted either to the negative or positive poles. Then, thought Davy, the elements themselves must somehow be electrically positive and negative. It would take over 100 years to see how absolutely marvelous Davy's suspicion was. As we shall see, the nature of the elements themselves and their positions in the periodic table are both the results of the marvelous electrical charges, but we must be patient. As wonderful as Mr. Davy's discoveries were, there were brambles of confusion that had to be cleared away before chemistry could advance further. So into the thickets we go. All right, see you tomorrow. Bye.